Hello everybody, this is again the MATLAB and Simulink Racing Lounge. As we can see, in today's session we again have a guest. I have invited guests from AMZ Racing at ETH Zurich, and we are going to talk about lap time simulation, which is a must-have for your concept decisions. So now let me introduce you to our guests in that session. Welcome very much Fabrice, Oehler and Philipp Föhn from AMZ Racing at ETH Zurich. Could you please introduce yourself briefly?
Yeah, sure. So my name is Fabrice Oehler. I'm in this year's AMZ Racing Team, and I'm responsible for the vehicle control unit, the lap time simulation, data analysis, and the sensors. And this is...
I'm Philipp Föhn. I was in the last year's team. We built the car Grimsel, and I was basically did the same thing as Fabrice is doing now, so lap sim and vehicle control unit.
Okay, perfect. So thank you for joining that session. Thank you for having you here. What can we expect from today's session? So we are going to introduce the topic of lap time simulation in general, a bit about the theory. Then I'm glad to hear about the AMZ approach, how you're doing that. You also promised to do a software demonstration. After that, we are going to have a talk about the advantages and pitfalls of that approach. And then I would like to conclude the session. So thank you, gentlemen, for joining. And I would say the stage is yours.
Thank you.
So first, a little bit about our last car. Grimsel, our most successful car, had four wheel hub motors, each one providing about 26.5 Newton meters and peaking at 37 kilowatts. This all with a weight of 3.4 kilograms. As accumulator, we used lithium polymer cells with a total energy of 6.46 kilowatt hours, about which we will talk later on. We have an aerodynamics package with a drag reduction system, and also we implemented a very new kind of adaptive damping system. We also used MATLAB and Simulink for the controlling algorithms for this one. And as a vehicle control unit, we use hardware by ETAS, which we also program in MATLAB and Simulink.
Okay, perfect. And you don't have to be so humble about that project and about that car. And you've had a pretty successful season 2014, right?
Yeah. We went to 4 events and won 3 of them. And we could also hold our world ranking #1, so it was very successful, yeah.
Congratulations, this is quite impressive. And seems that a 4-wheel car with aero package is right now the way to go. Let's see what the next season brings up. Thank you very much for that introduction on Grimsel.
Yeah.
So we want to talk a little bit about the motivation to use lap time simulation. So with our lap time simulation, we can predict the energy usage which our car is going to have. We can decide on different powertrain concepts, identify aerodynamic sensitivities to choose the right aerodynamic setup. Then we could evaluate the use of a DRS system, a drag reduction system, and we also can take other decisions like find the optimal gearbox setup, such as transmission ratio.
Okay, perfect. So to wrap that up, you basically need it for 3 purposes. First of all, it's about concept decisions. So you want to decide whether you need an aero kit or not. Then you want to predict energy usage during races. And then what I've also seen that you're using it for rather special decisions about gearbox transmission ratio. What would you say is the most dominating factor why you are doing lap time simulation? So the only reason or the one big reason why you are doing that?
Maximizing points.
Yeah.
Okay, very good answer. Perfect. Okay, at the end you say it's a must-have tool for obtaining a high number of points in the competition.
Yeah.
Good. Well, that should be motivation enough. Thanks.
Good, so we would like to talk a bit about the theoretical model which is behind our lap time simulation, as the car model which is behind the lap time simulation. So our simulation is based on a two-track model, which is actually based on a single-track model and extended with a second track. So we can simulate a four-wheel car. It's not.
But still, sorry to interrupt, it's a analytical approach. So there's no rocket science behind. It's, well, simple physics assembled in a two-track model.
Exactly. There are simple kinematic relations which are used to simulate, to model a car.
Okay.
Yeah. And with this approach of the two-track model, we can we include yaw movement, and the tire forces are implemented good enough to take decisions. And although it's not as complicated and as accurate as a four-wheel model, it's also complicated enough or accurate enough to take concept decisions.
Okay, well, it perfectly makes sense to me, and perhaps let's judge at the end what the model can do good and what can be improved. But at that point, it totally makes sense. Perfect.
So one very important point of our lap time simulation and also of the modeling of a real car is the tire data. It's very important to take the tire data into account because all the forces are delivered to the track over the tires. So we have in our lap time simulation in the car model our own tire data, which we get by tests, and there we can calculate the lateral and longitudinal forces Fx and Fy out of the normal force Fz, the slip angle and the slip ratio. The tire data is implemented by lookup tables. Yeah, so it's based on measurements with real tires.
Okay, real tires means you have taken your own tires and tested it. How can I imagine that? Have you a partner, an industry partner for that, or are you doing it on your own?
We have a partner. They have a tire test track. It's a big truck where you basically have assembly that can hold a tire and push it to the ground, move it around, and measure all the forces.
Okay, perfect. So just a comment from my side, even if you are a team who has not access to a tire test bench, there is the TTC, the Tire Test Consortium. And if you need more information about that, we have another episode of the Racing Lounge particularly focusing on tire modeling. But totally agree, it perfectly makes sense, or it's a must-have to access tire data for vehicle simulation and also for lap time simulation.
Exactly. So now we would like to show you how the workflow in lap time simulation works. So we have our car parameters where all the parameters of the cars, like the length, the mass, etc. are saved. Then we take these car parameters and to simulate.
I'm very sorry to interrupt right at the beginning of the slide, sorry. About the car parameters, you mentioned mass and length of a car, so I imagine this is rather easy to obtain. But in general, how much time do you have to invest in order to obtain the car parameters, as they are the foundation of the entire workflow?
Sometimes you need quite a lot of time because tire data is very difficult to get. There are motor parameters which are not that easy to get. For example, torque curves, etc. There are your losses, which are very difficult. There is a moment of inertia, which is not that easy to get, and so on.
Okay. Okay, but at the end, you need that data to go on in your workflow, right? Okay.
Certain data is not that important, so you can just approximate. Certain parameters are very important, so you have to know them exactly. Okay. Or you even want to change them because you are evaluating something.
Okay, got it. Perfect, thank you.
So then we take these car parameters to simulate one lap in our lap time simulation, and out of that we can also simulate whole events We can simulate endurance by driving like 16 tracks, or we can simulate an acceleration run by driving a straight track. And then with all this data, we can calculate a whole event. We can calculate the points which we would get out of the different disciplines, and also the points out of the whole event. And then we can analyze our data and visualize the different concepts to take concept decisions.
Just a question out of curiosity. You say you can calculate points. As far as I know, points are given by the organizers also with respect to the teams showing up. So the best team gets a very high grade. So do you use certain data from experience to calculate the points, or is it a strict mathematical scheme provided by the organizers?
It's always calculated in relation to your opponents. So we have like a standard set of opponents which we derived once at the beginning when we start to simulate, and then we can use that to spreaden up the field of opponents and get realistic scores.
Okay, good. So basically you're creating your own set of opponents and get the results at least qualitatively.
Yeah.
Okay, good.
So now we come to the lap time simulation itself, to the model overview. Perhaps we can start at the bottom, the driver. The driver actually is just a controller which tries to drive down a line.
Okay, well, a driver in an actual Formula Student car is also nothing but a controller who tries to be between the cones.
Yeah. Exactly. It's the same here, just it's not a human, it's a controller. And then the driver inputs like the steering, the throttle pedal and the brake pedals go on and into the controller. The controller holds all the vehicle dynamics and controls of our car. Normally we have there the vehicle dynamics controls of last year's car. So the controller then calculates the torque which is given to the different motors, and then this is passed to the powertrain and the tires. There we have modeled the rear and the front axle and the different tires to calculate the forces which are applied to the tires, and these forces are then passed on to the two-track car model, which is actually only kinematic relations which present the two-track car model which we presented earlier. And then out of these relations we get the accelerations and the speed, which then is passed back into the driver to recalculate the whole thing.
Okay, basically what goes back to the driver are also the results that you obtain from the simulation, so the tables, all the points and times.
Yeah.
Okay, perfect, good.
Good. So now we would like to come to a little bit of demonstration of our lap time simulation.
Sounds very good. Please, very interested in that.
To MATLAB now. First, we see here the same as we saw before on the presentation. This is the top layer of our lap time simulation. At the bottom here we have the virtual driver, the controller over here, then the rear and front axle, the forces, and the whole two-track car model.
Okay, can we have a look at, for example, front or rear axle, just to get an imagination of how you put together your model?
Yeah, sure. So we can take a look at the rear axle. So we see here the model of our motors. We have the wheel speed, which goes into this lookup table. So here the maximal possible torque is calculated out of the motor curve.
Okay, quick question on that. You obtained the motor curve via testing, or is it just a model approximation of that?
None of both. We develop our own motors and we simulate them, and so basically before the motors are built we have a very accurate torque curve.
Okay. And as you said, you're modeling them. Is it trustworthy data? So is it accurate?
It is based on magnetic simulations, so with the real physics behind it, and this is pretty accurate, yes.
Okay, perfect. That's a massive approach. Very interesting.
Yeah.
Okay.
So then out of this lookup table we get our torque, and this torque is then saturated by the values which come out of the vehicle dynamics controls, so the optimal torque for braking and for acceleration.
Okay.
And then this is passed back into these kinematic relations to calculate the wheel speed again.
Okay. What I also see at the right now, there are some lookup tables. What are they representing?
Exactly. So on this side we have our tire. So by calculating the slip ratio and the wheel normal force, which comes from here, we can calculate our tire forces.
Okay, perfect. Thank you.
Good. So perhaps we can take a little look in the kinematic relations of the two-track model in these dynamics blocks. So what you see here is a very simple approach to model the kinematic relations. We have the different steering angles to calculate the acceleration of the car by a simple kinematic relation. So we have the different forces, and which are summed up and then divided by the moment of inertia,
Or by the mass.
or by the mass, yes, depending on the kinematic relation we're using, and then we get out of this the acceleration.
Okay. And by integrating obtained accelerations, you get the velocity, and based on that, you can calculate lap times and all the data you need, right?
Yeah, exactly.
Okay.
So now we would like to demonstrate how this whole thing works. So we change to MATLAB. We already made a simulation with the normal Grimsel car parameters, which is this result 0. And now we would like to change two aerodynamic coefficients for lift calculation, and we would like to see what is the difference and what result do we get then.
Okay, and I have to say this is also a quite realistic situation. You have a certain starting point, and now you want to evaluate what changes on your aero package will result in lap time.
Exactly. Yeah.
Okay.
So I changed the parameters now.
It is CL high and CL low. We use two values because we have a DRS system, so we can change them in respect to activation of the DRS system.
Okay.
Exactly. Now with these new values, we resimulate our lap.
Okay.
And then depending on the hardware you're using, it is taking a little bit of time. Here on a dual-core PC we have around 40-50 seconds to simulate one lap. For an endurance it's little bit more, and for acceleration it's only several seconds to calculate the results.
Okay, are you already using parallelization of your models?
Yes, we do sometimes when we do like endurance simulation or concept simulation where we test several cars against each other. Then we do parallelization. We have one very powerful computer where we can simulate like 16 models at the same time.
Okay, well that perfectly makes sense, and already the model seems to be ready.
Yep.
Yeah.
Perfect.
So now we can compare the lap time which you get out of the different setups. And what we see here with the new setup, we are around 1 second faster on a lap, which takes 74 seconds.
Mm-hmm. Well, which is already quite a bit.
Yeah, and we can also see the energy which was used for driving. Yeah, we can also see the energy which was used for driving this lap. And what you see here is that we use a little bit more of energy.
Okay, sorry to interrupt here. What is the unit of that number here?
Kilowatt hours.
Kilowatt hours, okay.
And what we see here is that we use a little bit more energy, which is normal because we generated more downforce.
Okay.
And so the car needs at high speeds more energy.
Okay.
Yeah.
Okay, but this gives a pretty nice overview about the results, the structure of the results you get out of the lap time simulation.
Yeah.
This is good. Thank you.
Good. So now we like to come back to the presentation.
Mm-hmm. So what do you do with this information?
Exactly. What you see here in this plot is the velocity plotted over the track. It's Hockenheim in this plot, and the yellow colors are the higher speeds and the blue colors are the lower speeds. Another example of the results which are generated of the lap time simulation is the energy simulations which we made last year. So we simulated for an endurance the required energy of Grimsel at 6.3 kilowatts an hour. Then the accumulator of Grimsel had 6.5 kilowatts an hour on board, which was because of packaging reasons that it was a little bit more. And the energy which we used then at Formula Student Germany was 6.2 kilowatts an hour, which is pretty close to our simulated energy.
Exactly, I was about to say exactly the same. So 6.2 versus 6.3 kilowatt hours. So this gives quite a high credibility in your lap time simulation.
Yeah. I have to add to that we always talk about the energy used from the accumulator without the energy from recuperation.
Okay. That
So
means in an actual endurance race you end up with having more power in more energy in reserve.
No. It means that all these values are just like the values from the total energy subtracting the recuperated energy, so that we always talk about the energy taken from the accumulator.
Okay, got it.
So now what also is very interesting is if we compare all these different concepts, like in this table we have four-wheel driven concept with aerodynamics. The upper half is with a normal aerodynamic setup. The lower half is with an aerodynamic setup with a drag reduction system. And for each one we have simulated multiple energy levels.
Okay.
So what we now see from this one is the highest total score. So the highest score in all dynamic events is at between about 6.1 6.3 kilowatt hours for energy carriage. If you go down, you have not enough energy to really drive powerful through a whole endurance. But your car will be lighter. If you go up, your car gets heavier and heavier and heavier, and this also affects the points, and so you get somewhere an optimum.
Okay, so the optimum is about between 6.1 and 6.3 kilowatts carried in the accumulator.
Yeah, simulated with our driver and our parameters, yes, but this can vary very strongly.
No, for sure. Saying just for your special situation here.
Yeah. So what we also see between the concept without drag reduction system and the one with drag reduction system is that we in the end we have a difference of about 20 points. So the drag reduction system gives you 20 points more over all dynamic disciplines, while being 1 kilogram heavier. So we take the mass also in respect.
Okay. Okay. So what is the main reason? Where is the big benefit of the DRS? So where do the points come from at the end?
Basically, you save energy on the straight, fast lines. Therefore, you can save energy in endurance. You got more energy to spend accelerating out of corners, and therefore you get better times.
Okay. And you always have the energy or the power limitation in mind that is given by the rules, right?
Yeah, for sure. Yeah, it's always restricted at 85 kilowatt hours, or for next year at 80 kilowatt hours.
Okay, well, perfectly makes sense, because if you have a certain amount of power at your disposal and you have a car with less resistance because DRS is activated, you will speed up faster. Okay, makes perfectly sense. Mm-hmm.
So in this chart, we have visualized the results. On the left half, there are the cars with rear wheel driven cars. On the right side, we have the 4-wheel driven cars. For each one without aerodynamics, with aerodynamics, and with aerodynamics and the drag reduction system. Okay. And also with the varied energy levels.
So basically, let me ask the question. What we are seeing at the bottom line is numbers from 5.5 up to 7.1. So is this the energy you're carrying in your battery pack?
Yeah, this is the energy in kilowatt hours.
Okay, perfect.
And what we basically see here, that with our parameters in our simulation, we for the low performance concepts, we get decreasing points with more accumulator. So basically the car gets heavier, but it can't use the energy.
Okay. Mm-hmm.
But with the high performance cars, so the one with the 4-wheel driven and the aerodynamics kit, they can actually profit from the extra energy until a certain point. So until 6.1 or 6.3 kilowatt hours, the points are actually rising, and then the car gets too heavy and they're falling down again.
So another example of the use of lap time simulation was the endurance lap time versus efficiency simulations. So we made a simulation with different energies in our accumulator. Okay. Then we simulated the lap time which we have to drive an endurance. We simulated the used energy and the recuperated energy to calculate the efficiency score. And what we saw there is that the lap time score is decreasing much faster with decreasing energy than the efficiency score is increasing. So we see this in the plot below. The green line is the total score, and with decreasing energy we are losing points, although the efficiency score is increasing a bit, but it's increasing too slow to be better than the lap time score. So what we get there as a conclusion is that for an endurance, for our setup, it's the best to use all the energy we have in our accumulators and not to drive slow to get a better efficiency score.
Okay, well, makes sense. In your situation here, efficiency doesn't matter so much.
Exactly.
Or at least the points you get for efficiency.
Yeah.
Okay.
Good, so we come to the summary. Our lap time simulation is used mainly for aerodynamic setups to simulate the amount of energy which we should take in our accumulator. We can also use it to simulate transmission ratios. Then it provides accurate simulations of the energy usage and also the power restrictions which we talked before.
Okay.
Although the two-track model is not perfect, it's limited on rough concept simulations, so the whole suspension isn't modeled in our two-track model. And for more detailed simulations and also for rough concept simulations, we would need a more detailed model to get accurate results.
Okay. Well, completely understanding that. No model is perfect, and right now it seems that you are thinking about extending it to a more complex but also more powerful model, right?
Yeah.
Okay. Let me ask the question from the perspective of a team that wants to start with lap time simulation. Do you have certain recommendations for them? Should they go with an easy, simple mass or one mass model, go with a single track model, or go with a complex multi-body system, for example, from the beginning? So what could be a smart strategy to start with?
For starters, I think a very simple model is much better, because in a complex model you definitely lose yourself. You have so many parameters and it's hard to get it working, and therefore with a simple model you can already do quite fundamental concept simulations, and therefore the gain is definitely bigger if you start slow with an easy model. And then after you have some experience with that one, you can build your more detailed one.
Okay, so it's crucial to start simple and extend
Yeah.
it carefully.
Yeah.
Perfect. So last but not least, thank you very, very much for your efforts, for your time, and for all the material you've presented. I think for me it was very interesting, and I can imagine that it's also very interesting for teams thinking about that or already doing that. Let me now say a few concluding statements about what I think you have presented. So from my point of view, it's an almost perfect example that shows the benefits of modeling. I think this is a nice situation where you really showed why modeling is beneficial, because it actually helped you to make decisions. So as it is common for simulations, they require test input, data input, so entire data has to be determined. So it always comes with an effort, and it always necessitates a verification. So, and I think you have done it in a very nice way, checking the real situation, a real outcome on the track, compare it with the simulation results. And Philipp, I totally agree to what you've just said. Simplicity is key. So even with a single or two-track model, very, very helpful results can be generated.
Yeah.
So I think I'm pretty much done. I don't have anything to add. Do you have certain comments on that session?
No, it's okay for us. Thank you.
Perfect. The same. Thank you very much. It was a pleasure talking to you. And now let me conclude that session. We are right at the end. If you want to have a look at other episodes of the MATLAB and Simulink Racing Lounge, just go to mathworks.com/racing lounge. You will find other very helpful information on our Formula Student webpage, which is mathworks.com/fsg. And one thing that is really important personally to me, if you have feedback on that session, if you have questions, if you want other topics to be covered, let us know via our team email address, formulastudent@mathworks.com. And if you want to use MATLAB or Simulink in your team, we feel happy to provide you with a license. We have a complimentary Formula Student license offer, which you can find also on our webpage. And if you do use our software, we would be happy if you reflect our role as sponsors on your documents on your car. Perfect. That brings us to the end of today's session. Thanks for watching and see you next time. Bye bye.